Hi guys, welcome to tutorial 2, question 1. Let's do this. Like the other videos, pause the video, read over the question, give it a try yourself, and then we'll go through it together. Alright, so for this question, we gotta use structural induction, but it's similar to our, good old simple induction, and where they both start with a base case. In this scenario, it says that for any natural number that is bigger than or equal to 1. So can we make n equals to 1 with distinct powers of 2? Distinct over here meaning, no duplications, meaning 2 to the power of 0 cannot happen multiple times. But like I just said, 2 to the power of 0 is equal to 1. So therefore, n equals to 1 can be written as the sum of distinct powers of 2. So that's our base case. Then it comes down to our inductive step. For our inductive step, we're going to start with our inductive hypothesis, and that's pretty much our assumption. We're going to make an assumption that let there be an m, aside from the n that the question already gives. The question already gives n, the variable n, to be a natural number. I'm going to choose another one, m. M is going to be between 1 and n. It can also be, m is going to be bigger than or equal to 1, and it's also going to be smaller than or equal to n. I'm going to put something here for that because that was a tongue twister. And our assumption is that every number from 1 to m can be written in as the sum of distinct powers of 2. That's our hypothesis. So the automatic next step going to be, well, let's prove the same thing for m plus 1. Let's see if the same thing happens with m plus 1. Well, the way I went at this is that there's two cases. One, m plus 1 could equal to 2 to the power of something. That's just, just a case that might happen, right? Let's say m plus 1 is going to equal to 2 to the power of 3, or 2 to the power of 4, or whatever, something. And in that case, it already is written in the sum of, it's already written as the sum of distinct powers of 2, right? 2 to the power of something. Or the second case is going to be, all right, m plus 1 is going to equal to 2 to the power of something plus something else. That's a tongue twister. I'm going to again put that right there, but just to say it again, the second case is going to be m plus 1 equals to 2 to the power of, let's say, k, for some k, plus some remainder, some extra thing right there. And in the second case, when it's m plus 1 equals to 2k plus the extra, right? We already know 2k is a power of 2, right? So it just comes down to proving if the extra, that little, let's call it e, if that is also the sum of powers of 2, because if that's the case, then both of these guys are going to be sums of powers of 2, and making the m plus 1 to equal to sums of power of 2. So the e right here, if you really think about it, because we already know what m is, and it's already distinct power of 2, m plus 1 equals to 2 to the power of k plus e, right? In the worst case scenario, 2 to the power of k cannot equal to 0, because if it equals to 0, that means that e is going to equal to some number that's bigger than m, and we don't know if that can be proved, right? And even so, e can also not be 0, because then it's going to be m plus 1 equals to 2 to the power of k, which we already proved that in our first case. So 2 to the power of k has to be at least 1. So which leaves us with, e equaling m. But if e equals m, we already know it's the sum of power of 2. So in that case, m plus 1 can be written in sums of base of power of 2. Now, in the event that 2 to the power of k is not 1 and it's bigger than 1, it means that our e has to be between 1 and m. And based on our inductive hypothesis, we already know that we can make every number between 1 and m a sum of distinct powers of 2. So therefore, we've covered our bases. 2 to the power of k is already in the power of 2, and the e in whatever it is, right? The extra, it could be between 1 all the way to what we just talked about. It can also be written as sum of distinct powers of 2. So therefore, because these two things are being added together, m plus 1 is going to be written in the sum of distinct powers of 2. And by proving that we can, by proving that m plus 1 can be written in the sum of distinct powers of 2, we have finished proving our case. And that's pretty much it. That's the end of the question. Alright guys, that'll be all for this question. I'll see you guys in the next video.